Hey, I'm going to give you some notes here for some more info about universal gravitation. In particular here, we'll start with some energy for universal gravitation situations. What do you need to know? Well, the first thing we need to know is how do we quantify, how do we set up our mathematical model for universal gravitational potential energy? We know that, for example, local gravitational potential energy is equal to mgh. And you have to pick a 0 point, but we just usually pick one that makes sense for whatever context we are working in. The thing that really matters is the change in gravitational potential energy, which is still going to be true for us. And we know that the potential energy in a spring, 1/2 k x squared, those are the two important potential energies for us in thinking about mechanical energy. Sometimes we're given some potential energy function. We can use that. And I want to remind you also that, of course, local gravitational force is negative mg, and spring force is negative kx for an ideal spring. So the question is here, oops, should be a capital G. What's this? Well, I know what this is, right? This is negative g over r squared. And I know how to get from these to these, right? This is a calculus relationship. If you look at what's going on here, in all of these cases, the derivative of the potential energy function with respect to position, I'm going to put an x here, but here the position was measured, we used h because it's vertical up down. Here I did in fact use x. Here our position is r, right, the distance from center of object. So in all of these cases, or these two, we can see that that's true, right? The derivative of this is equal to this with the addition of a negative sign. So that means that the derivative of this must equal that. So derivative of ug with respect to position, so I'm going to call this r here, is equal to negative, oops, sorry, not ready for that yet, negative g m over r squared. Going to do the integral thing in a second, right now in fact. So if I want to get back to ug, I just have to do some antiderivatizing here. Not really a word, that. So antiderivative of this gets me back to this. Okay, now here, the negative gmm, oh, wait a minute, negative, so that's already there, so I have another negative sign here. So sorry, I lost one of my negative signs while I was trying to correct my error there. So there's already a negative sign that comes with this, so I need to add another one here, so that's going to make that positive. Okay, so when I do the antiderivative, this is the variable, gmm, that's all constant. So I'm going to move the constant to the outside of the integral, and then r squared on the bottom is the same as r to the negative 2 dr. Okay, what's the antiderivative of r to the negative 2? It's negative r to the negative 1. So So there it is. Now, a few comments about this. Comment number one is this is on your equation sheet, so it's not a thing. You don't need to be able to go through this process to derive that relationship. This is along with this. Those are like the two things that are on the equation sheet for universal gravitation. There's lots of stuff that isn't, that we do need to know how to derive. But this is, so you can drop that wherever you want. Some comments. The fact that it came out to be negative is might be somewhat unsettling to you because this is negative energy. Of course, this is a constant, 6.7 times 10 to the negative 11th. These are two masses, and this is an r, which is distance from the center of whatever object here. So those things are all positive. So this is, in fact, going to come out to be a negative number. It's a negative amount of energy. What? What does that mean? Well, remember, just like with our local gravitational potential energy, the thing that's important in problem solving is not some like fixed value of what this is. What's really important is how much this changes. And the choice of an h value is very important for us here because everything is measured in terms of that. And just like here with our local gravitational potential energy, if I was going to drop something in my classroom and I picked the zero height to be the ceiling of the room, then I would have a negative height, a height that was below that. This would be a negative value. And I'd get a UG that was negative. And you'd be like, well, that wasn't a very good choice. Well, maybe not, but it would work fine because what really matters is how much the change in potential energy, how much the local gravitational potential energy changes, not what it's like some set value. And that's going to be the same for us here. So one way of understanding why it is this expression is because of this r on the bottom, there isn't an r value that we could choose that makes this equal to 0 and that would give us like positive amounts of potential energy, except for if we let r approach infinity, if we say that the amount of universal gravitational potential energy is 0 at infinite separation. That's effectively what we are doing here, right? Then when this goes to infinity, this goes to 0. So it's kind of like if you have, let's say if we're talking about our sun, and here's like the Earth, how much universal gravitational potential energy is there at this location here? How much does the Earth have? Well, it has this much, right? Negative gmm over r. And if you were going to take the Earth and move it further and further away, then eventually when you get to infinite separation, this is where you have 0. And notice that as you come closer, the amount decreases, right? It goes from 0 universal gravitational potential energy to less than that. It goes into the negatives. But we say that it's 0 at infinite separation. I'm going to show you in a minute how you can use this kind of consideration and how you're going to have two different values of this. So maybe that will help it make a little more sense, how we use it in practice. Okay, so let me turn the page on that. For a circular orbit, we know that the velocity is equal to the square root of g m over r, where m is the central object, the thing that's being orbited. If you don't remember where that comes from, you could look back at your notes. I've actually got them right here. That came from these notes here, where we set these two things equal to each other, and we did a little bit of algebra, and we got this result here on the way to getting Kepler's third law. Okay, so this is not on the equation sheet. That is something that you need to be able to derive, but I'm not going to redo that for you. If that's true, then the kinetic energy that something has in circular orbit, well, kinetic energy is just 1/2 m. This is the small m. This is the thing that's orbiting, not the thing in the middle. That's the middle thing. Times 1/2 mv squared. So velocity of orbit is this. So the kinetic energy of orbit is, simplifying all this, we get g m m over 2r. And I want to point out to you the similar forms of these. Right? This is negative gmm over r, this is gmm over 2r, but aside from the negative sign here and the constant on the bottom here, we have a gmm over r. Right? This one is on your equation sheet. This one is not. So if you needed to know this, you need to know how to go through that process. It's a short process, but you need to know how to do it. If you were ever asked what is the total mechanical energy of orbit, well, total mechanical energy is just potential energy plus kinetic energy, right? So it'd be the sum of those two things. All right, so let's see. What else do I need to tell you? I think for orbit stuff, that is all you... Oh, no, that's not true. So one more thing before we start digging a hole to the center of the Earth. What about escape velocity? This is a thing that we need to know about. First of all, what does it mean, escape velocity? Well, that's the velocity that it would take for something to go from the surface of some planet. We could say the surface of a star, but of course if you're at the surface of the star, you're not going anywhere because you're toast. So from the surface of some planet, and if you're at the surface of some planet, you're already at some distance r, right? So from there to here, where r is infinity. So in other words, what velocity would something have to have so that it could make it to infinite separation, so it could separate itself forever from this? What is that minimum velocity to just barely get there? Well, there are no non-conservative forces here, which means mechanical energy is conserved. So here, what do I have for kinetic energy? Kinetic energy, I would have 1/2 mass times whatever this escape velocity is squared, and that's what I'm trying to find, right? I need to launch this thing with a lot of speed to escape from this planet. How much gravitational potential energy do I have? Dang it, I wrote the small g again. Big G. How much universal gravitational potential energy do I have right here? Well, I've got negative g m m over r. Okay. When I get to infinite separation here, how much kinetic energy do I have? Well, if we're just barely going to get to infinity, that seems a little bit like a fuzzy concept there, but we want to just barely get there, which means when we finally arrive at infinity, I don't need to have any kinetic energy anymore. Just like if you were throwing something and trying to figure out something about its maximum height, that's where the velocity is 0, so you wouldn't have any kinetic energy there. And what about gravitational potential energy? Well, by definition, the amount of gravitational potential energy I have when r is infinity is 0. So when I finally get off to infinity, I have 0 total mechanical energy. Okay, so because there are no non-conservative forces, that means mechanical energy is conserved. So that means whatever I start with, which is 1/2 m times escape velocity squared minus g m over r, that's my total energy here, is equal to the total here. And if I solve for escape velocity, it is that. That is not something that is on the equation sheet. So you need to know how to set this up and derive this. It is not hard to do at all. It's just the 1/2 mv escape squared is equal to, or minus gmm over r is equal to 0, and then you solve for escape velocity. That's it. Maybe worth noting that the velocity of circular orbit and the escape velocity are only different from each other by the square root of 2. This times the square root of 2 equals this, right? And the square root of 2 is about 1.41, so this is only about 40% more velocity it takes to escape forever than it takes to orbit. So that might give you, some idea how delicate the orbit situation is. If you boost your velocity by much, you're really going to change the orbit by a lot. So there's plenty of care that needs to be taken, let's say, when you want to put something, satellite or whatever, into circular orbit around the Earth. It's very, very touchy. So, again, only 40% difference between escaping forever and being in a nice, stable circular orbit. Okay, one more thing I want to tell you about here. The first thing GRV, what does that spell? Gravitation inside some kind of sphere. We're going to start with a hollow sphere. And this I'm going to just have to tell you, and you're going to have to take my word for it, but I'll try to explain at least why this could possibly make sense. Inside a hollow sphere, so like if you had, imagine that there was like a giant ping pong ball, and all of the mass of it was basically like this big shell, and you were at some location on the inside. How much gravitational pull would you feel being inside of this hollow sphere? Well, let's see. You would feel some from like this part of the hollow sphere, right? And if gravitational force is gmm over r squared, then I guess the r is a little bit smaller. You're kind of closer to this, so you'd feel a little bit more tug from this than you would say from this piece over here, but then there's this piece and there's all these other parts of it. And how would you possibly like add them all up? Well, it's like adding up infinitely many things. Let's see, adding up infinitely many things. What does that sound like? That sounds like an integral. But it's not an integral that we need to know how to do because it's three-dimensional. It's a multivariable calculus problem. And that ain't something we know how to do. So you're going to have to take my word for it that the math works out just so that no matter where you are inside the sphere, the sum of all the gravitational force on you, the pull in all the different directions, it adds up to 0. That's pretty obvious for if you were right in the center of the sphere, that you'd be pulled equally in every direction and that all those pulls would cancel out and the net force on you would be 0. So here, it turns out that the math works out that all the force sums to 0 no matter where you are inside the hollow sphere. So that's interesting and cool. So what if you're inside a solid sphere? Like you dug a tunnel trying to get to China or whatever, and you were down here at some location, let's call it small r. Well, you could imagine that there's like a smaller piece of this planet, or whatever it is, here, with radius, oh, that was supposed to go up to here, so I guess we're here, sorry, my radius came out a little bit too small. And the whole thing, the whole planet, we'll say, has radius big R. So what if you're here? Now, there isn't actually another ball inside it, but I want you to imagine that there is, because everything outside, everything that's at a radius greater than r, small r, from you, is like a whole bunch of spherical shells around you, and the net force from all of those is 0. So there's no net gravitational effect or force on you from all of the stuff that's outside the little radius r. All of that cancels out. So if you just went to the bottom of a well, say, that was, I don't know, let's say 10 meters deep, then at the bottom of that well, you would experience slightly less gravitational force there because the outer, like, 10-meter layer of crust of the Earth would not affect you anymore. Now, of course, the Earth is kind of lumpy because of mountains and stuff, and it's not perfectly spherical anyway, so that's such a small distance, that 10 meters, that it would be not appreciable. But you could imagine getting deep enough where it would make a difference. So how much gravitational force is there at this position r? So at this distance r from the center, we only get gravitational force from the inside. So in other words, from the smaller, I'm going to say smaller planet, of radius r. So let's see if we can figure out, I'll put a expression on that. So how much is there? Well, there's g. I'm going to leave the negative sign off just because I'm not really interested in the direction of it. I just want the magnitude of it. You could put the negative sign on there. You could leave it there. It doesn't matter. It's just telling us the direction of that force, that it's toward the center. So g m, and that m is the mass of like the little version of the planet, and then here's u, or whatever object is down there. So gmm over r squared. Right? Now, is it possible to figure out what the mass of that planet is relative to the mass of the whole big thing, which we'll say the whole big sphere has a mass of big M? If you remember from geometry, if you have three-dimensional figures, the ratio of the volumes of them is proportional to the cube of any linear measurement. So in other words, if you have, let's see, just a little bit of scrap paper here. If you have a cube of side length 1, and you have a cube of side length, ooh, that's a funky looking cube, of side length 2, then the ratio of the volumes is 1 squared v small to v big is equal to the linear measurement 1 cubed to 2 cubed. It's 1 to 8, not 1 to 2 or even 1 to 4. So if we assume that this is a uniformly distributed sphere, which of course most planets are not, but our simplest version of this model, if we assume that it's uniformly distributed, then the mass and volume are directly proportional to each other. So the mass of the big one is to the mass of the little one as the radius of the big one cubed is to the radius of the little one cubed. Because geometry, three-dimensional stuff. Okay, so that allows me to simplify here and put this in terms of constants. So if I like cross multiply and do all that, I get g, and then here it would be r cubed over big R cubed times big M, and then that little m is still there, over little r squared. And then simplifying this, everything in this is a constant, g m over big R cubed, and then I've got an r cubed here, little r cubed and little r squared is equal to that. So that's interesting. So this whole thing is a constant, and this is just r to the first power. So that means if you started out at the very, very center of this and then worked your way to the outside with r increasing, the little r increasing all the way until you got up to big R, then the amount of gravitational force you feel is just a linear, it's first power linear dependent on that distance. So if we wanted to make a graph of how much gravitational force there is at various locations where r is like the radius of a planet, then and if you go from the very center from like r equals 0 up to the radius of the planet, then this just increases a straight line where the slope of it is this. And once you get to the surface of the planet, how much gravitational force is there right there? There's g m over r squared, which of course is exactly what you get here when you plug in big R. It should be big R. And then what happens after that? Well, after you get to the surface of the planet, then our regular old universal gravitation model takes over, and we get the inverse square relationship. So by the time you got to here, it would be like 1/4 of what it was there, and then by the time you got to 3R, it would be like 1/9 of what it was. So it does the inverse square thing from there. And that is all I have for you in this set of notes.